All right. Algebraic manipulation is a big thing that we want to be able to do, and now that we've come up with some properties for these exponential logarithmic functions, we'd like to be able to manipulate those a little bit. So if you're looking at your note page, you should see these same problems on here. So we're going to look at changing some forms of these things. So this is clearly in an exponential form to begin with here. Maybe make that a little slightly more visible on this. And we want to change that into the exponential form. But if you remember, the way that that works, we have our y equals b to the x is the exponential form, and x equals log base b of y is the logarithmic form. And so this does not quite look like that exponential form yet. Okay, we've got to have that base by itself. It's this 5 that is the problem here. So we're just going to divide both sides by 5, and we'll get that 3/5 is equal to 2 to the 4x plus 1. Okay. This now does look a little bit more. I can identify everything in here. I can say that this is the y, and the 2 is the b, and this up here is the x. And so rewriting in its exponential form, it will look like 4x plus 1. That's my x part, is equal to the log base b, which in this case is a 2. We have that common word base between these that really identifies where that goes, of 3/5. And if you had a calculator that did log base 2, you would now be able to solve this, subtract 1 from both sides, divide by 4, and get an x equal. But this is all that it asked for at this point, was to change it there. And the key thing, again, was there had to be some manipulation at the beginning of the type that we've been doing for several years before we could get it into the proper form. Okay. This one looks a little more exciting over here. Again, if we want to change this into its exponential form, then we've got to get it to a place where it looks more like this to begin with. So just a single logarithm with an argument after it and something else on the other side. Okay. Well, we got logarithms here everywhere, but we can deal with those. The first thing that I'm going to look to deal with is I've got this 2 there, and I can't have that in front. If I try to divide it over, then it becomes a problem with these other things in here. But this looks like the 2 maybe ended up there because it used to be an exponent out here. So I could start by rewriting this as 2 log base 3 of x equals log base 3 of 2x plus 4 squared. Now, I mentioned the thing about not dividing by the 2 before, but the reality is that still, I could do that and probably still get to a valid answer on this. So there's lots of different ways that we can approach this. I'm going to subtract the log base 3 of x from both sides, just because my target here is to have just a single logarithm on one side, and this is 2 of them over here, and that would give me a 3 equals log base 3 of 2x plus 4 squared minus the log base 3 of x. But I've got 2 logarithms with the same base and subtraction in between, and I add the division property. It looks like somebody did the division property to it there, so I can rewrite this as 3 times the log base 3 of 2x plus 4 squared over x. And now it fits my pattern over here. This is my x from the formula above. I've got the log base 3, there's my base, and all of this stuff is my y. So rewriting it as y equals, I get 2x plus 4 squared over x. Y equals b, which is 3, raised to the x power, which is also 3. And so this now looks more like the kind of functions that I would have dealt with before, but again, it was just a matter of rewriting this in its exponential form, and that's how we do that. That's my final answer on that one. This, of course, was my final answer over here. Okay. All right, changing bases. Okay. This one takes a little bit of extra thought here. So we've got a 5 to the x minus 7, but what if we wanted to write this as a power of 10? Okay. Well, the tricky part here, and I'm just going to kind of cut to the chase. Actually, I think what we'll do is, looking at this, we want to write this as a power of 10. So somewhere in the back of my head, my question is, can I write 5 as 10 to some power? Okay. Is it possible to do that? Well, if I rewrote this in its logarithmic form, right? It would say that the log of 5 is equal to y, right? This is a common logarithm. I don't have to write the base 10 because this was base 10. So this is telling me if this y is log base 5. So it says 5 is equal to 10 to the log base 10 of 5 power. So if I replace my 5 with a log to the log base 10 of 5, or log to the common log of 5, then this becomes 10 to the log 5 all to the x minus 7 power, and I know with my properties that means that is 10 to the log 5. In fact, I'm going to, just so there's no confusion about where things are, I'm going to put the x minus 7 first. This is a power to a power, so I'm multiplying by log 5. If I write it the other way, I might think that the x minus 7 is inside that common logarithm, but it's not. So this now is exactly the same thing as 5 to the x minus 7, but it's written as a base 10. Okay, I might want to do that because you may be staring at a calculator that has only one logarithm button on it. Okay. And, well, obviously for an exponential problem, you probably have the buttons that you need for that. But it leads us to this problem over here, and maybe I'm staring at a calculator that does not have a log base 6 button. So how do I use the only logarithm button that I've got? Okay. Well, let's do the same kind of thing here. We can take the 2 out in front right now if we wanted to, that's fine. Or we could look at just this log base 6 of 81 part. And let's do that. Let's take a look at the log base 6 of 81 and see if we can write that as a log base 10. Well, if we said it's equal to something, right, then we could rewrite this in its exponential form, and it would say 6 to the y is equal to 81. And then using what we did on the other side over here, we know that 6 is the same thing as 10 to the common log of 6. Okay. So we could rewrite this as 10 to the y times the log of 6. And that's equal to 81, but now we have a base 10, so if we did a common log, if we rewrote this in its logarithmic form based on the common log, where this is our b, and this is our x, and this is our y, then we're going to get y, or x equals, so y times the common log of 6 is equal to the log base b, that's our common log, of 81. And so now we can say, well, the y, which was my log base 6 of 81, I could write as the log of 81 over the log of 6. And so my original expression then is 2 times the log of 81 divided by the log of 6. Okay. Probably even could do a little bit more manipulation in there, but that has rewritten it as a common logarithm. Okay. And I'm going to throw in here that there is a formula for this. Okay. Called the change of base formula. And the change of base formula for logarithm says that the log base b of y is equal to the log base a of y divided by the log base a of b, the old base. Okay? And we can see that happening in here. We chose to go to a log base 10, so we did the log base 10 of 81 and divided by the log base 10 of 6, which was the old base. So this is our change of base formula. Got a couple more things on the note page here. So we're going to come back to the change of base formula here in a little bit. For this, I'm writing using a common base to try to come up with a solution. This is a problem we should be able to do without a calculator. That's kind of the point of this. And when I look at the bases that are there, 4 and 32, I should recognize those both as being powers of 2. So I'm going to rewrite 4 as 2 squared to the x over 2. 32 is 2, 4, 8, 16, 32. That's 5. That's 2 to the 5th power to the x plus 1. Okay. But these are power to a power rules, so I should multiply the exponents together, which is going to give me 2 to the 2 times x over 2 is equal to 2 to the 5 times x plus 1, but that's just 2 to the x is equal to 2 to the 5x plus 5. Now the insight that I'm supposed to have at this point is that I've got both sides say 2 to a power, okay? And if they are supposed to be equal, then the only way that's going to happen is for their powers to be equal. Technically, I'm taking a log base 2 on both sides of this. If I do the log base 2 of 2 to the x, I get an x. If I do a log base 2 of 2 to the 5x plus 5, I get a 5x plus 5. Subtracting 5x from both sides, I get negative 4x is equal to 5. So x is negative 5/4. And I was able to solve this without a calculator. It would look like a fairly complicated problem, but if x is negative 5/4, then both sides of that equation are going to be equal to each other. Okay. And then finally, this is a tricky little problem, okay, that I'm giving to you here because I don't want it to end up being tricky. So it gives us a couple of bits of information. We don't know what base b is, but we're told that log base b of 8 is about 2.0461, and log base b of 3 is about 1.0810. And we want to know, what is the log base 3 of 8? Can we possibly get that from here? Okay. I'm going to bring that change of base formula down here. Okay. So here was our change of base formula. What I want is a log base 3 of 8. All right. So I lost the, this was a b in here in the formula up above, log base a of b. Okay. Well, if I'm looking at what this is, the log base 3 of 8, if I said this was my b and this was my y, and I tried to plug them in over here, it would say I can do the log base a of y, which is 8, over the log base a of 3, which is my b, log base a of 3. So this should be equal to the log base 3 of 8 according to the change of base formula. But if I just change these a's in this equation, or in this expression, into b's, which I'm just searching, it's a variable, right? If I want, so log base b of 8 divided by the log base b of 3 should be equal to the log base 3 of 8. And I know that the log base b of 8 was 2.0461 approximately. And I'm going to divide that by the log base b of 3, which is 1.0810. And so on my calculator, if I do that, I find that that is about 1.8928. I'm going to write that a little bit cleaner, 1.8928. And so we're able to get kind of this unexpected information here where we didn't know what the base was at all, but we're able to find a logarithm without actually knowing that base. Now we could do log base 3 of 8, we could do log base 8 of 3, it would just be doing the division in the other direction. So there are some examples of ways that we can use these new properties that we have available to us to manipulate expressions, and depending on how far you go in math, you may be asked to do that more and more often.